It's my pleasure to introduce our first speaker today, Dr. Yogesh Ramadass. Dr. Yogesh Ramadass received his B.Tech degree from IIT Kharagpur and the SM and the PhD degrees from MIT, all in electrical engineering. He is currently the Director of Power Management R&D at Kilby Labs, Texas Instruments, where he is involved in research and product development efforts, looking into high power density and low electromagnetic interference automotive and industrial switching converters, small form factor converters for consumer electronics, nano power IoT designs, and high voltage power systems. Dr. Ramadass was awarded the President of India Gold Medal in 2004, the Electronic Engineering Times Innovator of the Year Award in 2013, and the Young Alumni Achiever Award by IIT Kharagpur in 2018. He was a co-recipient of the Best Paper Awards at CICC 2018, ISSCC 2009, and ISSCC 2007. He is a senior member of the IEEE and serves as the chair of the Power Management Subcommittee at ICC and as a distinguished lecturer for the IEEE Solid State Circuit Society. He serves as an associate editor of the IEEE Journal of Solid State Circuits from 2015 to 2018, and on the Technical Program Committee for the IEEE Symposium on VLSI Circuits from 2016 to 2018. The title of his talk is High Voltage Devices, Topologies, and Gate Drivers. So please join me in welcoming Dr. Yogesh Ramadass.
Okay, thanks, Tina. Thank you very much for the welcome. I'm really glad to be here in front of you guys to present on high voltage devices, the corresponding topologies, and the requirement of gate drivers in these applications to drive the future energy landscape. So before we get started, let me talk a little bit about the recent growth in semiconductor electronics and the need for power as we move forward. Semiconductor electronics, as you have seen recently, has just grown exponentially, and the devices that we use on a daily basis, the semiconductor content on them has also grown quite a bit. What used to be almost $0 in semiconductor content for a basic bulb has now grown into more than $20 with all the smart bulbs and LED drives that we have today. And the story is the same when it comes to automotive electronics, which has seen exponential growth in semiconductor content. A 1970s car, which had around $65 of semiconductor content, now has somewhere close to $500. Okay, no wonder there's been significant growth in the semiconductor companies and their revenues of late. And the story is the same as we go for basic industrial electronics. What used to be pretty simple sensors, mechanical or electromagnetic, has now gone into more semiconductor-based sensing. Your cooktops, the drones, there's been a lot of new applications that has come about that's really driving the exponential growth in these devices. Okay. As the devices and the semiconductor content grows in all the applications around us, so does the need for the power. Okay, we've got to power all these electronics, and power electronics, we touch upon it on an everyday basis, right? From the chargers that we use to power our cell phones, to the smart LED bulbs that we use at our homes, to the solar panels, the motor drives in our car. All of that requires significant amount of electric power to be driven. Okay. In this chart, what I'm showing is the electricity or the primary energy consumption for the whole of the United States. Okay, and it's in quadrillion BTUs. It's a huge amount of energy. When we look at the power that's been used, 40% of that energy is basically electric power. Okay, Out of that, 30% used to flow through a power converter before it reaches the end application, meaning you have energy or power obtained using one form, and before it could be used in the electronics, it needs to be converted. It needs to be massaged into the right voltage and current levels. And it flows through a power converter before it gets there. Now the prediction is by 2030, 80% of that electricity would be flowing through a power converter. Okay? So that puts a tremendous burden, and not just a burden, but an opportunity for us to improve upon not just the efficiency, but the density and the cost of these power electronics. Such a way, we could meaningfully control the energy consumption in this world and reduce more of the emissions that we have. Okay, so that's a lot of power that's going to be flowing through electronics, basically made up of devices and magnetics and capacitors. Okay, so anything that we can do to improve upon the efficiency of this is going to have a significant impact in the energy landscape of the world. Okay, let me briefly walk through what a power electronics landscape looks like. It's a very broad area. So today, what are we going to cover? I'll explain that in this slide. Power electronics can start from extremely low voltage levels for your IoT sensors, a few hundred millivolts of voltage, a few microwatts of power. We've got a talk later in this session that's going to cover IoT electronics. The 5-volt area is something that we are well familiar with, right from wearable electronics to our cell phones that we carry, stuff that's powered out of the lithium-ion battery. We're talking about a few milliwatts to a watt of power, our Class D audio supplies and all that. We go one level up, we've got the 12 to 48 volt electronics, laptop batteries, data center power. All of that is between that voltage range, and we're talking about tens of watts of power in this case. And then you go one level further up, and we've got our offline power that we derive from our wall outlets, 240 to 480 volts, and even further up on a HEV, EV, we go talking about 1200 to 2400 volts. Okay. This talk, I'm going to primarily cover from 50 to 1 kilovolt subset of voltages, the devices that we use, the applications in these in that voltage range, and the power topologies that are used. Okay. There are going to be other talks in this session. As I mentioned, there's going to be IoT, there's going to be wireless power that's going to talk about the low voltage spectrum. There's going to be an automotive electronics talk that's going to talk about the 12 to 48 volt spectrum too. Okay, so I think it's a pretty well balanced session, I would think, where we'll cover the entire landscape here. Okay, so when it comes to high voltage and power electronics, the central component is the power device itself. Okay, the improvements in power devices is what has been driving the growth in power electronics over the last few decades. It all started with the silicon control rectifier as the primary power device in the 1970s, and very akin to the improvement in our micrometer and nanometer scale electronics for CMOS. There's been a similar kind of change that's been happening in the power electronics world. The power device is central to any improvement in a power electronics application, and so from the silicon control rectifier, the development of the power electronics MOSFET and BJTs, leading to, in the 1980s, end of 1980s, the IGBT era. Now we'll talk about what these things mean over the course of this talk. And the superjunction MOSFET, and over the last decade, the introduction of wide bandgap semiconductors, from silicon carbide to gallium nitride. These have been driving the growth in the power electronics space. And if you look at specifically the area that's seen the strongest growth is in this, well, they call it low voltage. Of course, voltage is very relative. I mean, if you talk to an Intel engineer, 3.3 volt to 5 volt is high voltage to them. In this case, low voltage is classified as 480 to 1200 volts, and medium voltage is 1.2 to 1.8 volts. That's where the most significant growth has been happening, and this talk is going to primarily focus on that area. Okay, so before we jump into the devices and the topologies, let me get you a brief teardown of what a typical power electronics system would look like. And this is something you guys are well familiar with. It's just a charger for your laptop. Okay, it's an 85-watt converter. Most power electronic systems would follow a similar set of key blocks. Okay, starting from the AC line that you're going to hook up to, goes through an EMI filter. Okay, because we're talking about tens of watts of power switching. Okay, a lot of this gets injected back to the line, and it's going to affect everything that's hooked up to that line. So most of these components are going to come in with the front-end EMI filter to prevent switching spurs from getting back into the line. Okay. Following that is a simple bridge, a full bridge, which converts the AC to a DC voltage. Following that is a boost converter with power factor correction, and we'll talk about what these terms mean through the talk. And the energy is then stored in this big electrolytic capacitor before it's down converted to a 48 or 12 volts that can go into your laptop. Okay? So the central thing in this topology are the devices themselves. These are high voltage devices on the boost converter and on the LLC converter. And then you see that a lot of the space is really occupied by the magnetics and the electrolytic capacitor. Okay? So anything that we have to do to improve the density, the central thing we target is really going to be these passive devices. You can see the EMI filter itself is almost 30% of the area of the entire charger. Okay, so through this course of the talk, we're going to touch upon the devices that are being used in high voltage electronics, the kind of topologies, the buck and the boost and the flybacks, these kind of topologies, we'll touch upon that. And we'll talk about the drivers that are used to drive these devices and the protection that's needed in them to keep this entire thing safe. Okay, so that's going to be the outline of my talk. So to start with, let's go into the devices themselves, and we'll start with what is an ideal power switch. Okay, the ideal power switch, irrespective of voltage, you want to have a certain characteristics. It needs to block as much voltage as possible when it's off. It needs to be able to carry a lot of current with very little drop. It needs to be able to turn on and off very fast. And ideally, we'd like to drive it with very little power. And for high voltage systems, of course, we would like a normally off device. Okay, you don't want to be plugging into your wall adapter and the device being on and bad things happening. And of course, cost plays a primary role in any of these applications. But the real switch that we get is far from ideal. There is plenty of forward voltage drop across it. The turn on and off take its own time, leading to losses. There is leakage when the device is off, and the amount of voltage that the device can handle is limited, and it has a significant impact on the resistance of the device. Okay? So, over the next few slides, when we talk about the devices, we'll see how these non-idealities come into picture and what are the recent trends in the device electronics itself to improve upon and to make the device as close to ideal as possible. The first device that we're going to talk about is a power MOSFET. Okay? Not very dissimilar to what a regular CMOS device that we are all familiar with. It's got a gate, source. Well, we're looking for the drain here, but the drain is actually at the bottom. Okay, so that's the fundamental first main difference being the power MOSFETs typically are vertical devices, okay, to handle the voltages that we need. Okay, the gate side construction is still fairly similar. You got a P plus body region, you got N plus source contacts on either side. It's a symmetric device, and you got the drain region, which comprises of two main parts. There's a huge drift region across which the entire voltage drops, and then there's the N plus substrate, which kind of is typically backside metallized to come down to the drain connection. Okay? And one major difference also compared to a regular NMOS device that we're familiar with in the low voltage domain is the body is typically, the source contact is very strongly tied to the body. Okay, so you don't get that as the fourth terminal. So So that leads to an inherent body diode that is always formed between the source and the drain. And we'll see how this diode is used in typical applications. Okay, and why that strong body connection is needed, again, we'll talk about it when we look into the parasitics of the device. So when you look at this kind of a device, the central parameter for most of these devices is the resistance of the device for a given voltage that it can handle. Okay, the low voltage devices that we are well familiar with, there is almost an equal distribution between the three main regions that I'm going to talk about: the channel region, the epi or the drift region across which the voltage drops, and the final contact region, which is to the substrate before you come out of the drain. Okay. Now, at the low voltage side, for 30 volt load devices, there's almost an equal distribution between the channel, epi, and the substrate resistance. But as we go into higher and higher voltage devices, the key thing that changes is the drift or the epi region. This is the region that needs to grow to kind of block the voltage. Imagine that when this device is off and the gate is pulled low, and let's say it's a 600 volt device, between the source and drain, we're applying 600 volts, or rather, between the drain and the source, okay? That entire voltage needs to be blocked primarily by this drift region, okay? No wonder then the resistance contribution of that drift region significantly increases as we go to higher and higher voltages, okay? So in the typical vertical power MOSFET, the drift region is one of the key things that determines the RDS on of the device, which in turn defines its performance in power electronics. Now, in a typical vertical power MOSFET, as the drift region grows, not only does the width have to increase, but the doping also has to be in such a way that the electric field can drop across this entire drift region. So what that leads to is, as we go to higher voltage devices, you have this nonlinear characteristic. The resistance grows for every doubling of the voltage. The resistance grows by 3 to 5x, because not only does the width of the drift region need to, or the depth of the drift region needs to increase, but the doping is also have to be adjusted to block that entire voltage. Now, in the 1980s, there's another device that was introduced called the superjunction MOSFET, where you don't have this large columns of these P plus body regions. And what that allows you to do is break the bottleneck between the doping and the drift height. Essentially now you'll be able to dope the drift region much stronger because you can sustain the electric fields using these deep P plus columns. So that breaks the bottleneck, and what it allows you to do is have a linear characteristic between the breakdown voltage and the depth of the drift region. So that allows you to have superior resistance characteristics for a given voltage handling capability. Okay? So from that point on, superjunction MOSFETs have been the bread and butter of most power electronics devices. So if you look at the parasitics in this kind of a device, again, not very dissimilar to what we expect from a regular low voltage CMOS device. You still got your, as I said, the channel resistance, you've got the drift resistance. The reason to have the strong connection between the source and the body region, especially in a high voltage device, is to prevent the debiasing of this BJT. We're talking about real high voltage devices here. Any amount of resistance in this path can significantly shunt this voltage here and lead to really bad characteristics of the device. So having a strong source contact to the body when minimizing that resistance prevents the turn on of this parasitic bipolar here. With respect to the capacitance parasitics, of course you've got the same gate to source capacitance. The gate to drain here, I mean, there's a significant overlap between the gate on the top and the drain region, and the depletion region on the drain, very close to the channel. And you've got all the parasitic diodes between the source and body. Okay. So if we just look at the equivalent circuit of the typical power MOSFET, as I said, there is no access to the fourth terminal, so you're always going to end up with this source to drain body diode, which will be always there. You've got your regular terminal resistances on the gate, on the source, and on the drain side. Depending on how this device, if it's a discrete device, depending on how it is packaged, there may be additional inductances on both the drain source and the gate side also. The capacitances themselves, the gate to source capacitance is fairly constant. It's defined by the area of the device. Whereas the gate to drain capacitance, which controls the turn on and turn off characteristics of the device, is highly nonlinear. We'll look at it in the next slide. Okay. So the key parameters that when you take a look at a discrete power electronics device, data sheet would be the input referred capacitance, which is a combination of the gate to source and the gate to drain, with the drain source shorted. The Miller cap, the CGD, and the output referred capacitance, which is the CGD combined with the drain to source capacitance. So if you really look at the typical data sheet, and I'm going to show you the data sheet of a 600 volt Infineon 225 milliohm device here, and these capacitances are listed out in a very prominent fashion in the data sheet because it almost defines the characteristics of the device. The input capacitance, the CISS, is completely dominated by the gate to source capacitance, which is more or less flat across the voltage, VDS. But the other capacitances are highly nonlinear. Okay, and these play a big role in the performance of the device. When we talk about the output referred capacitance, the significant nonlinearity in the drain to source and the gate to drain capacitance leads to this kind of a characteristic where it starts off 100x larger at the low voltage range, and by the time the drain to source voltage has reached around 20 to 40 volts, we're completely depleted in the drain region and the capacitance significantly drops off. Okay? The data sheet item that is quoted really quotes at this once the capacitance is dropped off at the high voltage range. So when you look at the data sheet and say it's a 14 picofarad device on the output side, the capacitance is really quoted at 400 volts of bias. Okay? And it can be very misleading when you actually design these circuits. Design topologies with these devices. We need to understand the entire nonlinearity of it to make the best possible decision on what device to use. There's two other capacitances that are quoted. Both are output capacitance. One is energy related and the other is time related. So what do they mean? There's 29 picofarad of energy related cap and 330 picofarad of time related capacitance. And what it comes down to is this. The time-related capacitance really determines the total output charge on the device. Okay, so effectively, you integrate this nonlinear COSS across the voltage range to get the total charge on the device. And a significant amount of capacitance at the very low voltage range means that the total charge in the device is really present at the very low voltage range, and then it completely saturates. Okay. And the energy-related capacitance, what that leads to is the total energy in charging up this capacitor from 0 to whatever voltage that the capacitance needs to block or the device needs to block. Okay? And that's obtained just by a simple integral of the COSS times voltage. Now, the two capacitors that were listed here, the effective energy-related output cap and the effective time-related output cap, they really contribute to, if you just wanted to understand, okay, at 400 volts, what's the charge of my device? Then you multiply that by 400 volts and you get 125 nanocoulombs, which matches up with our integral here. The same for a time-related cap, you get around 2.32 volts. Okay, the energy-related cap rather. Now, what would be undesirable here is, if you were actually operating this device at, say, 100 volt, and if you used this capacitance number to find out the charge, you'll be significantly off, okay? Because if you multiply that 313 by 100 volts, you'll get 1/4 of this capacitance, of this charge rather. Whereas the total charge in the device is really almost the same as in a 400 volt device. Okay, so you got to be really careful when you're looking at these data sheets of these devices and using these capacitance numbers, because they're actually really coded at a certain voltage. And the significant nonlinearity of the device means that you've got to look in and actually integrate the charge to get actual numbers here. Okay? The next big thing that really determines the choice of your topology is related to that diode that we have between the source and the drain. Unlike a low voltage CMOS device where you have access to the body node, here the body is tied strongly to the source. Okay? So whenever you go into reverse conduction, the body diode turns on. Think of a regular buck converter. As the low side device is turned off, the inductor current starts pulling charge and the body diode turns on. Okay? The longer the body diode is on, the more minority charges are stored in the device. Okay? Now, when you have to turn off this device and put a voltage across it, before the device can turn off, all this minority carried charge has to be taken out before the voltage can start, before the device can start blocking the voltage. Okay, and that is a significant point. Why? Because the amount of charge that's needed to be injected into the device to let it block is of the order of tens of microcoulombs. Okay, it's a very large amount of capacitance, a very large amount of charge that needs to be put in, and that charge is really dependent upon multiple factors. For how long the body diode was on, for how much current was being pulled through the body diode. Those two play a significant role. The third parameter that determines the reverse recovery charge is the rate at which we're pushing current into the device to turn it off. Okay, that's because if you give long amount of time to a diode, it's going to recombine and the minority carrier charges can be taken out that way. So if you want your device to turn really fast, which is when you'll have a large DIDT, the reverse recovery charge is also quite large. Okay, so you need to be spending a lot of energy to turn the diode off and let it block voltage. Why it's important, I will show you in a few slides why the reverse recovery charge is so important in a device. Okay, let's talk briefly about the MOSFET switching characteristics. This is very similar to a low voltage MOSFET. Most of you guys are familiar with this. When you turn on the gate to source voltage needs to reach the threshold voltage before which the device can start conducting current. Okay, as it reaches the threshold voltage, the drain current is going to start building up in the device. Okay, and once the device has built up enough drain current to support the inductor current, only then does the drain voltage start falling. Okay, so first the gate voltage has to go from the threshold to the plateau voltage for the drain current to match up with the current that you intend to push through the device. And then the device reaches the plateau voltage, at which point the drain to source voltage starts to fall. Okay, and this plateau region is determined by the gate to drain capacitance, and there is a certain amount of charge that needs to be pushed in. Once the plateau region completes and the drain to source voltage has fully dropped to zero, the gate voltage further rises to a certain set point where you can minimize the RDS on. Okay, so you've got the threshold voltage, you've got the plateau voltage, and the final gate drive voltage to have the minimum RDS on. This is not too dissimilar to our low voltage CMOS. The one key difference I would like to highlight is the plateau voltage can be significant because you're really dropping or letting the device turn on from 400 or 600 volts down to zero. So the amount of charge needed in the gate drain region can be quite large. And that's really shown here. So when you look at the characteristics of the device, again, this is a data sheet of an Infineon 225 milliohm device. It's a 650 volt MOSFET. You can see, you will typically see the gate charge characteristics shown in this kind of a plot. Again, on the x-axis is the gate charge, y-axis is the gate voltage. You ramp up the device all the way up to the plateau voltage where only the gate to source capacitance is getting charged, and that's up to 5 nanocoulombs, and that's mentioned as a gate to source charge. Once it reaches the plateau, the gate to drain voltage starts falling, and there's charge injected from the gate to drain, okay? Now, that's around 6 nanocoulombs or so in this device. Note that between 120 volt to 400 volt of drain voltage, there is really no difference in the gate to drain charge. And the reason for that is, if you looked at the gate to drain capacitance, it's highly nonlinear. Most of the charge again is in the low voltage space, okay? Once you finish the plateau, again you raise the voltage up, the gate voltage up to the final set point. These devices can handle 12 to 15 volts of gate voltage, okay? Because we're really talking about high voltage device, the gates are pretty thick, and you want to minimize the RDS on. So that's what the gate charge characteristics looks like for a typical MOSFET. Okay, so why do all these things matter? Why have I spent so much time talking about the basic characteristics? Okay, because when you take a regular hard-switched buck converter, which is still the basic building block of most power converter devices, topologies, all these terms come directly and affect the efficiency or the losses in the device, okay? The primary loss, we're all familiar with the RMS square RDS on loss, it's a conduction loss. The remaining are all related to switching, okay? The drain side switching is directly related to the QoSS, the total output charge of the device times the input voltage times the switching frequency. The reverse recovery loss is directly related to the reverse recovery charge times the input voltage times switching frequency. Okay? So these two terms are on the drain side. I mentioned that when we turn on and off the device, there is an overlap. The voltage and current overlap, and as a result, there is some overlap losses. And that is mentioned in the cross-conduction losses. And finally, the gate drive, we're turning on 2 switches at a time, every switching cycle, so that's 2 times QG times the drive voltage, the gate drive voltage, which could be 10 volts or so. So you can see clearly the RDS on, the QoSS, the QRR, the overlap time, and the gate charge. Those are the key terms of a particular device as it relates to the loss, because the switching frequency and Vin are what we choose. The RMS current is the output current that we want to kind of deliver. So why has there been such a big push or a lot of interest around wide bandgap devices? We've spoken about MOSFETs so far, silicon MOSFETs. The central reason being the larger bandgap energies of these wide bandgap devices. It comes from the name itself, it's wide bandgap. What does the larger bandgap allow you to do is handle larger electric fields in smaller area, okay? The ability to handle large breakdown electric fields basically means we can have a much smaller device to drop the entire voltage that the device needs to block, okay? So the breakdown fields being higher means for a given breakdown voltage, the specific on resistance of the device can be an order of magnitude lower. Okay, so that allows you to reduce the RDS on of the device significantly for the same amount of voltage that you can handle. There's a certain limit in the silicon devices, and that limit gets broken by silicon carbide and gallium nitride devices. On top of that, gallium nitride offers you higher electron mobility, and both of that, when you look at the current density and the power density of the device, the electric field and the mobility come directly into picture. The other point that I'd really like to highlight here is the saturation electron velocity. That directly translates to how fast we can switch the device on and off, okay? And when we talk about overlap losses, that's an important metric. So let's look into briefly how a gallium nitride device is constructed. It's very different from how a regular MOSFET device is constructed, okay? You start from a low-cost basic silicon wafer, and you put in a buffer layer, and that's to distinguish between to prevent the overstress of the lattice between the gallium nitride that you're going to grow on the buffer layer and the silicon substrate. So you grow a thin gallium nitride epi, okay? And once that epi is grown, an AlGaN cap layer is put on top of it. Now the piezoelectric polarization between the AlGaN and the gallium nitride epi really leads to the formation of something called a 2-dimensional electron gas, okay? And that is really the basic channel through which current is conducted in a gallium nitride device. The moment the AlGaN is deposited on top of the gallium nitride epi, this 2-deg is formed, okay? And then you put your source and drain contacts on either side of the AlGaN layer, and that forms your entire FET, okay? Now you look at this, it's now no more a vertical device, it is a lateral device. Current is conducted laterally from the source to drain, and the 2-deg is automatically formed, so it's a normally on device. The way to keep it off is to take the gate voltage negative with respect to the source, and you deplete the 2-deg underneath the channel. Okay, it's a normally on device, it's a lateral device, and the 2-deg leads to significantly lower RDS on, as I mentioned in the previous slide. I mentioned that, okay, when we're trying to deal with high voltage devices, even at low voltage ends, you don't want a normally on device. I mean, people would prefer a normally off device. I mean, you want to come in from an off state and then turn it on. So to get there, one way to get into a normally off mode is to deposit a PGAN cap layer on top of it, on top of your AlGaN barrier. Okay, what that allows you to do is kind of deplete the charge underneath, so you get a normally off device. And this is something called a gate injection transistor. Okay, it has a diode characteristics on the gate side. It does have current when the gate to source is biased on the gate side, but it's kept to a low value. There are quite a few companies now that develop normally off gallium nitride devices, and then it operates very similar to a MOSFET. You need to raise the gate voltage up to kind of form the 2-deg layer underneath. The normally off device, normally on device, on the other hand, when you have 0 volts on the gate, the 2-deg is automatically present, and you need to take the gate negative to deplete it and to turn off the device. Okay. So if you just look at the characteristics, the regular D mode or the depletion mode normally on device has a VT of around -8 volts or so, and the normally off E mode device typically around 1.2 to 1.5 volts of VT, and it can take a gate voltage of up to 5 volts across it. Adding all that PGAN to get a normally off characteristics, you do have to sacrifice a little bit in RDS on and the device characteristics. So there's other ways to get a normally off device, okay? And that's obtained using cascoding. So here you have a high voltage gallium nitride FET as a cascode to a low voltage silicon FET. The silicon FET can only be 12 to 20 volts, so it's a really low voltage FET, so its RDS on can be made much smaller. So here, you're going to just drive the silicon FET on and off. The gallium nitride FET source or gate is always tied to source. So how does this work? It's fairly simple. When you want to keep the thing on, you apply voltage to the gate of the silicon FET, so the source and the drain source of the silicon FET gets turned on, and the gallium nitride FET is normally on anyway, and so current starts flowing between the outside drain to source. But when you want to keep it off, you bring the silicon voltage down to 0, the gate voltage to 0. So what's going to happen is the intermediate node voltage is going to start rising, and as it reaches the threshold voltage, which is around -8 to -10 volts, basically when this node voltage rises to 10 volts, then the gallium nitride FET is turned off, and then it starts blocking the voltage. And then any increase in the drain voltage is being blocked by the high the cascode gallium nitride FET. Okay, and the silicon FET only needs to handle the 12 to 20 volts, as I said. So it's a really low voltage device. So this is another way, and a few companies use this structure to actually get a normally off gallium nitride device. So let's compare the characteristics. I mean, the wide bandgap devices come with a lot of promise. Does it really translate to reality? So here is a 600 volt gallium nitride device of similar RDS on, 150 milliohms, compared to a 600 volt silicon superjunction MOSFET. The high voltage capacitance is fairly comparable, but when you look at the low voltage end, there's significant difference. There's almost 10x difference between the gallium nitride and the silicon FET. Okay, it's hard to read from these kind of curves, so let's just plot the QoSS and the EoSS that I mentioned earlier. output related charge and the output capacitive energy. So if you look at the output related charge, the gallium nitride FET is actually almost 4x lower for the high voltage applications compared to the silicon FET. Okay, and that's where you get significant benefits in the total output charge that was needed. When we looked at the losses in some of the previous slides, we saw that the QoSS directly impacts the overall loss. So the almost 4x benefit in the QoSS is a significant feature for the gallium nitride FETs. On the EOSS side, not as significant. The energy related term, we're talking about microjoules here, and here it's fairly close. So it's important to remember this when we start talking about topologies. Okay, the other big change, okay, is reverse recovery. When we looked at the gallium nitride device, you saw there was a source, drain, two-dimensional electron gas. There was no doping. There is no inherent body diode present in the gallium nitride device. Okay, it's a symmetric device, so it can conduct both in the first and third quadrants. Actually, let me walk you through there one more time. Source, drain, everything looks symmetric. So if you want a normal operation, current flows from source to drain, but you can reverse conduct it and it can flow the other way also, okay, without the presence of a body diode. So what that means is, when you go from the first to third quadrant, there is no body diode conduction, there is no reverse recovery charge that's deposited into the diode. So before you want to turn off the low side device, you don't need to inject a significant amount of reverse recovery charge. And that's a significant factor. We're talking about 8.2 microcoulombs for a regular 600 volt silicon FET. There is still something called the reverse recovery charge in the GAN data sheet, but there's really no body diode. So this charge is just the terminal capacitance that gets charged up. Your capacitance current can also mimic itself as a reverse recovery charge, but it's 2 orders of magnitude lower. Okay, we're talking about microcoulombs to tens of nanocoulombs here. Okay, this difference is what leads to the ability to let gallium nitride devices switch in hard switch topologies. Okay, and then when you look at the gate charge comparison, again, here on the left is 200 volt gallium nitride device, in green to a 200 volt MOSFET device. Much lower gate charge, much lower gate drain charge. Similarly, for a 600 volt device, you look at the QGD, which is the gate to drain charge, it's so much smaller. The ability to have very little QGD, the QGD is what determines the gate to drain capacitance determines the turn on and off speed. So you're able to switch these devices much faster when you compare to regular silicon devices. And the lower amount of charge also helps reduce the gate drive losses. Okay, so I go back to the breakdown of the losses again. The device can have much lower RDS on because of the larger critical electric fields. Okay, so it's a better figure of merit device. The RQ product can be much smaller. It has much lower terminal capacitances. The QoSS and the QG, both are significantly smaller. So for the same switching frequency, I can have lower losses, or I can switch it at much faster speed. There is almost no reverse recovery, okay? So this loss completely goes away, and the overlap times can be much smaller due to the low gate to drain capacitance. So my overlap losses can come down. So every one of these losses can be significantly minimized by using a gallium nitride device, okay? And that's what we'll see when you get to the topology section. What does the ability to go to higher frequencies buy you? This should be fairly simple to understand. Both the inductor, the magnetic component needed in the switching converter, and the EMI filter can be shrunk. This is a typical 100 kilohertz inductor for the EMI filter. That's a 1 megahertz inductor. So you can get almost 1/5 area and volume. And that's true for the filter passives and the output passives. You can go to new topologies with gallium nitride where you had to use bulky capacitors and magnetics. You can go to all ceramic capacitors using multi-level topologies. Okay, that leads to a nice planar design, and that's the alternate benefit. Higher frequencies, newer topologies. This is where primarily gallium nitride is and wide bandgap devices are going to bring us the benefit. Before we go into topologies, I'll just briefly talk about two other devices. We've so far spoken about 600 volt. As we go to even higher voltages for HEV, EV, three-phase, motor drive applications, you need to handle 1200 to 1800 volts. The silicon MOSFET quickly runs out of room because of the trade-off involved in the epi region, the drift region, and the RDS-on. One of the central innovations in the 80s was the development of this insulated gate bipolar transistor. It combines the benefits of a MOSFET-like input characteristic and a bipolar-like output characteristic. Where it really shines is when you turn on this device, there is minority carriers injected in the channel or in the drift region, which reduces the resistance of the drift region for a given voltage handling capability. When it's off, you have a certain drift depth, but then the minority carriers injected into that drift region reduce its resistance. So for a given voltage handling capability, you can have a much lower RDS-on device using this IGBT tool. Okay. So this allows you to block very high voltages, carry large amount of currents because you get almost a minority carrier device with the bipolar characteristics on the output. The wide bandgap counterpart to IGBTs is the ability is using silicon carbide. This takes you much larger than 600 volts that a gallium nitride device can bring. It looks very similar to a vertical silicon MOSFET, except it's grown on a silicon carbide substrate with a silicon carbide drift layer. And the ability to handle high voltages due to the larger critical electric fields it can handle helps reduce its RDS-on. So where do these two devices play? The silicon carbide output capacitance looks very similar to a gallium nitride device, so not too different there. But where it really shines is in the high voltage space, more than 1200 volts. The IGBT, when you have to turn it off, it's a minority carrier device, so you've got to take the charge or flush the charge out before it can block. So you have a significant amount of turn off energy, almost 890 microjoules in this case. The silicon carbide MOSFET, the same high voltage device, can have almost 9x lower of energy. Okay, so really, if I break it down into the voltage spectrum, the 500 900 volt range is where the superjunction silicon device has long been playing, and its wide bandgap counterpart is the gallium nitride on silicon substrate, up to 600 volts. Okay, while the superjunction device has proven reliability and robust operation, it's really low cost. It does have large amount of output terminal charge and the reverse recovery charge. Gallium nitride, extremely fast switching. A lot of work has been going on to improve upon the cost of this device, and the reliability concerns are being addressed. So it's still a lot of work is ongoing in this space, but a lot of companies have released these devices, and there's going to be a lot of applications coming in the market very soon. Greater than 1 kilovolt is where silicon IGBT plays, and the wide bandgap counterpart in that space is the silicon carbide device today. Okay, so that's overall a brief description of the devices used in the power electronics space. So now let's go into what a power system topology looks like. We're going to talk about what are hard switch converters, what does soft switching mean, and we're going to talk about some hard switch converters and some soft switch converters. Okay. Briefly stop here. If there's any pressing question, I can answer it. If not, we'll leave it to the end. Okay. All right. So let me move forward here. Again, let's remember this loss breakdown here as we talk about hard switch converters. So how did I come up with these equations, and how does it relate to the operation of a regular buck converter? You got a high side device, you got a low side device, you got an inductor and capacitor. You turn on the high side, Inductor current ramps up, you turn on the low side, the current ramps down, and you keep switching it to get a regulated output voltage along with the control loop. When you turn on the high side device, okay, so just before turning it on, the inductor current was being pulled through this body diode in the third quarter, okay? Now, to turn on this high side device and to let the low side device block the high voltage, the first thing, as I mentioned, that needs to happen is you need to push charge into this diode, and that's what is shown here. Okay, we're talking about 5 amps of current being pulled by the inductor. But when the high side device turns on, it needs to support a lot more charge, a lot more current than the 5 amps. And where is this current going? It's really going into the low side device, first to replenish the reverse recovery charge, and then to bring up this capacitance from 0 to whatever the input voltage is. So both the QoSS, the output related charge of the low side device, and the QRR, which is the charge, reverse recovery charge of this body diode, is getting pushed in through the high side into the low side device. And all of that charge is coming from the input voltage Vin. And so that's where you get this energy loss, QRR plus QoSS times Vin. The turn off is different. When you turn off the high side device, the inductor current can discharge this capacitance from Vin to 0 before you turn on the low side. Okay, so that's actually a soft switching event because the inductor current is discharging that cap. Okay, so what's happening here, while the inductor current is discharging this cap, the energy stored in this cap, the EOSS of the low side, is going to the output. So that's a plus, that's not wasted. But there is some energy that's being used to charge up this inductor because now the high side device has to block the voltage. Okay, so it goes from 0 to Vin. So there's energy coming from the input, which is equivalent to the EOSS of the high side, and there's energy going to the output, which is EOSS of the low side. And these two typically cancel out if you use similar sized devices. So the final loss that you're left with is just this QoSS loss and the QRR loss times the input voltage, which got burnt across the high side device. So that's really the main hard switching loss in a buck converter. Okay, so now I'm going to just build a buck converter and walk you through some of the numbers. What are the typical numbers involved here? This is a 400 volt converter. I'm just switching it open loop at 50% duty cycle, so I'm going to get half the input voltage on the output. I'm using a 750 microhenry inductor with 170 milliohms of resistance, and it's around 2.7 to 2.8 amps of output current. So we're talking about 200 times 2.8, so that's around 560 watts of output power. Okay. The inductor current, of course, follows a nice a linear ramp up and ramp down. The efficiency I'm able to get is almost 98.2% with gallium nitride devices. Okay, and why am I able to get that? So I'm going to use a 150 milliohm high side and a 150 milliohm low side device. My RMS currents is, RMS square is around 7.7, so I get 0.6 watts of loss on the high side and the low side. Because I'm operating at 50% duty cycle, it's symmetric. So that's the conduction losses. Let's look at the switching loss. QoSS of the gallium nitride 600 volt device is 40 nanocoulombs at 400 volts, 100 kilowatt switching frequency, that's 1.6 watts. Overlap loss, which is the time it takes for the voltage to ramp up from 0 to Vin. Because the gallium nitride device can be turned on so fast, it actually ramps up in 8 nanoseconds, which means I went from 0 to 400 in 8 nanoseconds. 50 volt per nanosecond slew rates. Okay, supremely fast switching. Why is that needed? Because if I don't switch as fast, already with this switching rate, I get 0.67 watts of loss. Dead time, when I turn off the high side and I let the inductor current ramp down on this switch node, and okay, there is no body diode in a GaN. Okay, so the device actually conducts in the third quadrant. It starts conducting current from the source to drain, and that's what is shown here as the dead time loss. Instead of the diode, it's the VT of the device, average current times the amount of time we spend in the dead time, 200 nanoseconds, that gives 0.24 watts of loss. And the remaining losses are related to the inductor, just the winding loss and the core loss of 2.9 watts, to a total loss of 8 watts. Out of 560 watts, I lose around 1.6% or so I'm able to get close to 98.2% of a regular buck converter hard switching. Okay? Let me show a start number here. If I was going to do this with a silicon MOSFET, if I built this buck converter with a silicon MOSFET, just the QRR charge, the reverse recovery charge, is 700 nanocoulombs. Okay? I run through the numbers, it's 28 watts. Okay? The total loss of the entire converter with the GaN is 8 watts. Okay? So just this reverse, that's why the reverse recovery is so important. It doesn't allow you to build these kind of hard switch converters with MOSFET devices. Okay? Just some quick math on how I got the core loss calculation, if you guys are interested. Typically, when you wind these inductors on a specific core, in this case, the inductor that was obtained was wound using 45 turns on 2 cool mu cores. You would get these charts from the core manufacturers. So this is the core loss chart for 100 kilohertz cool mu core. What it shows is the flux density on the x-axis and the core loss, volumetric core loss, milliwatt per centimeter cube on the y-axis. The core manufacturer also will give you the mean length of the core and the cross-sectional area of the core. So all you have to do is, after you wound certain number of turns to get the inductance that you need, you calculate the max flux density, which is the peak current divided by the mean length times mu and n, and the min power flux density. The separation between those two is the flux density excursion on the core. And the way to read the chart is, when they say flux density, it's actually delta B by 2. So you get 260 Gauss. You go look at the equivalent number here, and you get 70 milliwatts per centimeter cube. You know the overall volume of the core, which is 8.33 times 1.64, and that's how you get the core loss. Okay, it's pretty important when you're really talking about high voltage applications. Out of 8 watts, 2.9 watts is on the core itself. Okay, so the ability to do this hard switching topologies, primary buck boost based topologies, what that allows you to do, PFC is power factor correction. For any wall adapter, any power that you get from the wall, if it's above 75 watts, you need to match the current and voltage profiles to be in sync, so you don't spend too much reactive power. Okay, that's what power factor correction is. Typically, you need greater than 99% of power factor. Okay, in this case, this is a conventional PFC boost which uses a MOSFET device. You have an input bridge, and since the reverse recovery loss is so high, what they typically do is use a silicon carbide diode on the high side, because that's the diode that matters for the reverse recovery charge. Okay. Now, silicon carbide again has very little reverse recovery, and so people have been using this kind of a boost conventional PFC for a long time. With the introduction of GaN now, what you can do is completely eliminate this bridge, and you have something called a bridgeless totem pole boost. Okay. And what that gives you is a 1 to 2% efficiency improvement, because you got rid of this bridge. And the ability to hard switch without reverse recovery charge is what makes this converter possible. And that basically, when you had a 96 and 97% efficiency converter, you can push it up to 98 to 99%. Every percentage matters, because these are the kind of converters that are going into your data centers, and all the racks, the millions of racks that are available there. Every percentage leads to lower thermal losses, leads to lower cooling requirements for your data centers, and that's why, I mean, these things are highly important. Okay, so that was hard switching. As we go into larger amounts of power, even the small amounts of QoS loss that are inherent in a gallium nitride device cannot be tolerated. So then we go into the next set of topologies, which are soft switched. What is soft switching? It's very simple. When you are turning on or off this device, you don't want the voltage and current waveforms to overlap. You either get the voltage completely to zero before you turn on the device, or you let the current drive down to zero before you turn off the device. Okay? How do we do that? Let me explain with a very similar, same kind of topology. Just a simple buck converter again. Okay? Just two devices, inductor, capacitor. But here, just by suitably controlling these devices, we're going to get soft switching. Okay? So just follow me here. Step one, high side is on. Okay? High side is on. You ramp up the inductor current. It ramps up. Switch node is high. Step two, turn off the high side device, but don't turn on the low side immediately. Okay? You let the inductor current, which was flowing, softly discharge this node. Both these devices are off, so this node is going to be softly discharged. And when that node reaches zero, that's when you turn on the low side device. Okay? So that's soft discharging. That happened even in a regular buck converter. The difference here, on the low side device is kept on for a longer amount of time, so the inductor current ramps down. It actually hits zero and continues to go negative. Alright? So it goes negative, so you reverse the direction of flow, and then you turn off the low side device. And you then don't turn on the high side device immediately. What you do is you let that inductor current push into this capacitor. So it's going to ramp up your switch node softly, and when it reaches Vin, that's when you turn on the high side device. So now you're turning on the high side device when its voltage across it was already zero. Okay? So you don't get those overlap losses. Alright? The other interesting thing to notice is that never was this diode ever turned on. Okay? So the diode never turns on in the third quadrant on the low side device. And that completely eliminates your reverse recovery charge. Okay? So that's what soft switching brings. But now you need to let the inductor current have a longer excursion. Okay, it has to go all the way from negative to positive. Whereas in a regular buck converter, you could have kept the ripple very small. Okay, but you're one in reducing your QoS and QRR related losses. All right. So how does the efficiency breakdown look like in this case? You still have the RMS square, the conduction losses. You still have the winding losses in the winding and core losses in the inductor. But there is no more the QRR loss, the QoS loss. The gate drive losses are still there because you have to turn on and off the device. Okay? So the switch related losses are related to QG, and the only other thing is related to RMS and the peak current in the case of the core loss. Okay? So does that mean now I don't need the gallium nitride device anymore? I can just use these topologies with silicon devices because I don't have any more the QRR and QoS loss. Well, let's take a look at it, right? Actually, the amount of current that you need to take the inductor current negative, the amount by which you need to take the inductor current negative is dependent upon the switch. Okay? To understand that, you looked at the inductor current waveform, it looks more or less triangular. So the I load, the load current is an average of peak and valley. So the peak to peak current, which determines the core loss, you can write it as a function of the valley current. The RMS current can also be written as a function of the valley current. But why is the valley current important? The valley current, at the point at which the valley current reaches, the current reaches the valley, what was happening is this device, this node voltage was at zero. So the high side capacitance was charged up. And then the valley current kind of pushes and charges up this node. So it actually charges the low side cap and it discharges the high side cap into Vin. So if you walk through the numbers, the energy in the system when you were at the valley, when you started, was the EOSS of the high side. But the energy delivered to the switches to charge up that switch node is proportional to the charge times Vin and the energy of the low side. So if you look through this, what you're going to get is the valley current is a function of the QoS of the high side. Okay? What that leads to means if I have a larger QoS device, in the case of silicon, I need to take my inductor current for the negative. I mean, it's fairly intuitive, right? If you have a larger capacitance, you need more inductive energy to push it back up, to soft switch. So that's how, in a second order fashion, the QoS starts impacting. In a regular buck converter, the QoS was directly impacting the losses. In a quasi-resonant buck converter, which is a soft switch converter, the QoS indirectly through the valley current impacts the efficiency. So here's some waveforms. Green being GaN and red being silicon for the same voltage devices. You can see that I need a larger swing on the silicon device. Same RDS on, same voltage, but the larger QoS means I need larger peak-to-peak excursion for the same load current. Okay? That leads to larger RMS currents, larger peak-to-peak, meaning larger core losses, and that's why you get an efficiency difference still, even though you're not directly related to QoS in losses. Blue is GaN, red is silicon. Okay? So directly quite a bit of efficiency change, almost 5%. Then you add the gate drive losses on top of it. The gate charge is only 2 nanocoulombs for GaN, it's 13.5 nanocoulombs for silicon, and it gets further separated out, the green to the purple. Okay? So even in a soft switch converter, the QoS means that gallium nitride is still superior to silicon. Okay? So now I'll talk about our third topology, and this is a bread and butter topology of all your low cost chargers that you have. Most of the cell phone, tiny laptop chargers, the USB chargers, which plug into the wall, 10 to 30 watts or so, has something called a flyback converter in it. Okay? Very simple topology, only one device, only one switch, low side FET. Okay? You come in from the line after the bridge, this is around 360 to 400 volts. You have a coupled inductor. It's not really a transformer, okay? It's a coupled inductor. And the difference being, there is no direct transfer of power from the primary to secondary when it's turning on. How it works, very simple. You turn on the low side device, you kind of magnetize the coupled inductor. You magnetize the primary, okay? The primary current builds up to a certain value that you'd like, and then you turn off the low side device. The magnetizing current initially pushes up on the switch node, it ramps it up to V in plus, let's say the turns ratio is N, it ramps it up to V in plus N times V out. At which point, across the secondary, now you have V out, and the diode turns on, and the secondary current then demagnetizes the inductor. So it'll come down to 0, and that's how energy gets transferred from the primary to secondary in the flyback. It's a simple coupled inductor, and once the secondary current completely demagnetized the coupled inductor, what's going to happen is the voltage here is V in plus N times V out. The voltage here is just V in. That is not a stable operating point, so the primary will just resonate down, okay, to let this voltage come down to V in. So it starts from V in plus N times V out, the settling point is V in, so it goes to V in minus N times V out, okay, and that's the valley point at which you turn on the low side. You've actually let the self-resonance of this inductor basically bring the switch node to the valley point, which is the lowest energy point, and that's where you turn on the low side device. So it's called a valley switched flyback for that reason, okay? Because the lower the voltage at which you turn off, this is the hard switching losses in the converter. Okay, that capacitance, the energy stored in it is just shunted to ground, so you want that voltage to be as low as possible. Okay, that's the coupled inductor in the system. Okay, that pretty much occupies the space in a typical flyback converter. So if you want your charges to be smaller and smaller, you want this coupled inductor to be really small. And the electrolytic cap is the other big component. Okay, but it's not as simple. There is always leakage. You never get a perfect 100% coupled system. There's going to be leakage inductance on the primary. That leakage, what it does is it prevents you from getting these nice waveforms. When you turn off the low side device, the leakage and magnetizing inductance, the energy in it pushes the switch node up. But once the secondary turns on, the magnetizing inductance, the energy in that can be coupled to the output. But the leakage inductance cannot get coupled. So what it's going to do is, it's just going to push this switch node voltage further and further up. Okay? If you just let it be, it's going to really destroy this device. So what they do is they put a clamp. It's a simple RCD snubber. Okay? So this clamp voltage will then come in and clamp the maximum voltage seen by the low side device. And then that leakage energy kind of just resonates down, gets lost in that RCD snubber, and the valley switching happens, and that's how it continues. But why that leakage inductance matters is because you need to set the clamp voltage suitably. Okay, the total clamp voltage, which is specified as VC here, that determines the maximum voltage seen by the low side device. So for a typical wall adapter, 285 volt RMS, you go to max of 360 volt at the input. This voltage is 360 volts max DC. You want a 60 volt output, and if you have a turns ratio of 2, another 120 volt gets impinged on the primary. Okay? So there's 360 plus 120, that's 480 to begin with, and then you set the clamp at another 120 volts above it to get a total of 600 volts. So that's how you can use a 600 volt device in this application. If you didn't have the clamp, then you would need a much larger voltage rating device, and that's not really economical for us. Okay? You walk through the losses. In this case, the flyback, it's the switch. There's only one switch. There's a lot of magnetic components. There's the diode. So you got the RMS losses in the switch, the diode, the winding and core losses in the coupled inductor. And the switch-related losses really in this case will come down to the energy in the switch. So that's why if you look at the overall losses just specific to the switch, it's EOSS related. And from before, what we've noticed is between the gallium nitride and silicon, the charge-related parameter is the biggest difference. The energy-related parameter was pretty close. And that's why you don't really see too much of an efficiency benefit in this case. When you use it in this flyback converter, you may as well just use a regular silicon device to get a good efficiency. Of course, there's a lot of other parameters because of the magnetics that bring down the efficiency of this kind of a system. But that's where we are when we talk about a flyback converter. So primarily, silicon or GaN in this topology does equally well. There's further, we talked about sub 100 watt. If you go to further, more higher power levels, the topologies change. I'm just putting this chart out there for information purposes. We won't have really time to get through most of this. Okay, so got another 15 minutes. So let's talk about, finally, about the gate drive requirements. We talked about the devices, we talked about the topologies. How do we drive these devices? That plays a central part. That also has a significant impact on the overall application. So typical gate driver, in this case again, it's a flyback kind of configuration. You have a low side drive. So you have a discrete MOSFET. Of course, in power electronics, we're talking about discrete FETs. You don't have all of them integrated. So you don't have the driver integrated in the same process as the power device. Because the power device is, in the case of a MOSFET, it's a vertical device. So there's no way you're going to have CMOS on it. In the case of a GaN, okay, it's a lateral device, so there is potential to have drivers integrated on the same substrate, but it becomes fairly complicated, okay? A typical driver is kept as a discrete device outside. In this case, I'm talking about a low side driver. Very simple, it's got input pins, and it has two output pins to drive the gate, one for pull up and one for pull down, and we'll see why that's needed. The customers externally can put some gate drive resistances for pull up and pull down. And the key parameters of the driver are really the internal pull up resistance it's got and the pull down resistance it's got. And the gate driver can typically handle from 4.5 to 18 volts. As I said, most of the MOSFET gates can handle up to that voltage. And you would like to drive it at a higher voltage to reduce the RDS(on) of the device. So you've got the pull up and pull down resistances, and you've got the speed at which you can turn on and off the device in terms of the rise and fall times. Okay, so how do you turn on and off a typical MOSFET, again, we've gone through this before. You raise it above the plateau, above the threshold voltage. Near the plateau region is where the switch node kind of slews up. Here's the reverse recovery current when the device turns on, and it flattens out into the output current. What determines the rate at which this turns on, the switch node turns on? And that's a very important parameter. For both efficiency reasons, you want this turn on to be very fast to minimize the overlap loss. But also, from an EMI point of view, EMI, as I mentioned, you have significant amount of filtering needed. The faster this goes, there's a trade-off. The more that switch node is going to radiate out, okay? Because it's directly related to the rate at which this node changes. And in the next slide, I'll show why reliability is also very important here. But before that, what really controls this slew rate? During the plateau region, the current that's coming in from the gate drive is what is used to the drain to source voltage as it drops when the device turns on. The CGD times that dVdt is the current that comes in from the turn on phase, okay? So the V drive, which is the input voltage, minus the plateau voltage, divided by the RG, is used to turn on the Miller cap. But at the same time, the drain current is turning on this, charging up this capacitor. So if you walk through the math, essentially the dVdt, or the slew rate of the switch node, is determined by the resistance of the gate and the GM of the device. Typically for these MOSFETs and gallium nitride FETs, the GM is very large. So the effective dVdt is just controlled by the resistance at the gate, which is why this gate resistance is typically given out as an access point, so the customers can choose the slew rates that they want to use this device with. Here's what happens in a non-ideal scenario where you have power loop inductance. So when you turn on, the switch node actually rings up quite a bit before it settles down. So this peak voltage is what the low side device needs to be rated for. So the larger you have, or if you turn it on faster, this inductance in the main power loop kind of lets this voltage ramp up significantly. And that leads to suboptimal devices that you would need to use. And this is where the gate drive control comes into picture. So you try to increase the gate drive resistance to reduce the slew rate because of the presence of significant parasitics in your power loop, and that reduces the ringing levels to a more manageable value, so you can use conventional 600 volt MOSFET devices. Of course, it comes at the penalty of efficiency, because now your slew rates have reduced and your overlap losses go up. On the turn off side, equally important, if you want to keep this low side device off when the high side is turning on, okay, this switch node is slewing up very fast, okay. What's going to happen is it's going to push current into the gate side of the low side device. So the pull down resistance is very important. It needs to be small enough such that this CGD dVdt times the combination of these resistors is lower than the threshold voltage of the low side MOSFET to keep it off. When we're talking about 600 volt, we don't want to shunt and short circuit these two and blow up the device. Okay, so this pull down gate resistance plays a significant role in that. And the drivers typically quote that value also in the data sheets. I mentioned the loop parasitics affects your efficiency. The two key loops, okay, high side, low side, there's the power loop from the input cap to the high side, low side device, and then there's the gate loop, okay. The power loop, okay, now the power loop we saw on the last slide. In the gate side loop, what happens is, if there is significant inductance in the gate to source path, as you're trying to turn on this device, when the drain current starts pushing up, there's a kickback from the common source inductance, okay? And it tries to turn the device off while you're trying to turn it on. And that leads to further reduction in the slew rate and increase in the overlap time. So here's the gate source loop. The larger the parasitic inductance in the gate source loop, the larger are going to be your losses. And similarly on the drain source loop, the power loop, okay? So As we get these nicer devices like gallium nitride, silicon carbide, which have the ability to switch very fast, if you do not control the parasitics in your external loops, the device is pretty much useless, okay? You're going to be limited by the parasitics, then why did you go with the gallium nitride device which gave you this ability? So, to make the best possible use of the device, what you really need to do is minimize these loops. So the construction of the driver with the power FET becomes extremely critical. Okay? So what I'm showing here is an actual 100 volt gallium nitride module. It's got the high side, low side devices. It's got the driver sitting right next to it on the same lead frame. Okay? What that allows you to do is minimize this gate to source loop, and this on the in-package capacitors that are placed right next to the device, so it kind of minimizes the high side, low side back through V in power loop. Okay? All of these need to be very tight for you to make the best possible use of the device. Okay? So that allows you to switch really fast with minimal ringing. Okay? So you can use lower voltage devices, and the reduction of those loop inductances gives you a much larger efficiency compared to if you use these devices discretely and had a discrete driver. Okay, so you can see the ability to package these devices properly lets you bring down the gate to source loop down to 190 nanohenries, 190 picohenries, right? And the power loop down to 300 picohenries. Okay. So finally, a couple of slides on isolated driving. I mean, I'd shown here that we're driving the high side device also using a single driver. How do you get to these high voltage levels using a single ground referred driver? Okay, that's where isolation comes in. Isolation as a concept, we've seen it in the flyback. The coupled inductor isolates the primary and the secondary. Similarly, on the gate drivers, you want a signal to go from the low side domain to the high side domain. So that's where isolation comes in. It's used either for safety, to break the ground loop between two separate distinct circuits, to communicate from one domain to another domain, and for level shifting. Okay? What are the primary ways a signal can be isolated to move from one domain to another? There's four main ways, four kind of parts that are typically in circulation today. One is capacitive. You can use a blocking capacitor to block the voltage and isolate. Of course, the coupled inductor is another inductive method to isolate. There's magnetoresistive, and then there's optical photodiode methodologies to isolate. Mainly, they differ in the amount of signaling rates that they can handle and the power needed to keep the link alive. All right. There's a lot of capacitive-based isolators coming into the market recently. They offer very good data rates over the isolation boundary, the ability to handle large isolation voltages, and the key thing, another thing is, when these devices are switching, they're switching at very fast slew rates. Okay, when the high side device switches, which means my gate here for the high side is, or the source is slewing up significantly, my level shifter needs to be able to maintain the integrity of the signal, and that's something referred to as common mode transient immunity. We're talking about isolators with around 200 volts of per nanosecond immunity available in the market today. Okay, so that as the devices switch fast, the drivers and the isolators that we use also need to be able to handle such switching speeds. So in the 5200 half bridge that I'd showed, the level shifting is really done using a simple capacitive methodology. There's a couple of ways in literature this level shifting has been done. As I said, one is just to isolate the low side and high side using drain extended MOSFET devices. So this is a DMOS based dynamic level shifter. You can use capacitors to isolate the voltage and have capacitive level shifters. And one very interesting work that was done a few years ago was using microwave couplers to couple from the low side domain to the high side domain, and this allowed very fast transient rates and very good immunity also. So there's multiple of these, just some references shown here. So with that, I would like to kind of summarize that high voltage devices have a significant role to play in our future energy landscape. The advent of these new devices, gallium nitride, silicon carbide, I think they have a major role as we try to reduce the carbon footprint, the energy footprint, as more and more things getting electronic. And the ability to have good topologies and the right drivers to drive these FETs and the deep understanding of those things will help us make use of these devices in the best possible way, leading to smaller and more cost-effective solutions. So with that, I'd like to conclude here and we'll open it up for questions.
Thank you very much, Dr. Yogesh Ramadass, for the very exciting talk. We have time for a few questions, please.
Sure.
I have a question. I saw that you had quite a few simulations that you have run.
Yes.
The models for these transistors, do you build them yourself, or can you get them from the vendors?
So for the MOSFET devices, SPICE models are available from the vendors. Yes, you can get it. And for gallium nitride also, people are developing these models. There is a central initiative to develop models for the gallium nitride device. There's a central repository to get some typical device models. And with the recent announcement of new devices in the market, yeah, you can get SPICE models to simulate these devices, yes.
What about applications in integrated controllers rather than just discrete devices? Is there progress being made there?
Definitely, at least on the, up to 600 volt, there have been few companies that are developing, well, when we say integrated, the maximum integration that's being happening right now is the driver with the power device in one substrate. That's the level of integration that's happened. Because beyond that, it becomes very cost prohibitive. I mean, the power device has a different set of masks, and the driver needs to have a whole different set of masks. I mean, you don't want to have this big power device using out all the masks of the driver. So keeping it discrete is more cost conscious, but having them on the same substrate does give you some level of flexibility and integration capabilities. Yeah. So it is happening.
Further questions?
I have one more question. You saw that for the MOSFET transistors, there is a gate plateau at the charging, turn on. You know that the IGBTs have similar plateaus as well. And these are due to the same mechanisms?
Yes, it's mainly due, the plateau is to get the drain source voltage to drop. Yeah, so the gate has to plateau when the current in the gate to drain capacitance gets discharged in this case, yes.
And that's when the reverse recovery is happening, am I right?
That's really when the reverse recovery is also happening, because that's when you're, well, the reverse recovery is supposed to finish before the plateau happens, because the diode, as you start building up the voltage on it, the reverse recovery has already happened. So the DIDT interval happens just before the plateau, and that's when the reverse recovery is happening. Yeah. Just before the plateau. From the threshold to the plateau is when the reverse recovery happens. Okay. All right. Thank you very much. Yep.